So we're going to do this combination lock problem. It has a lot of similarities with the design 2 that failed. The ASN circuit looks something like this. It has coming into it a enter button that's been debounced with this circuit down here. And then it has a correct button that comes from this circuit right here. It sends out its current state information to this combination check circuit. This is where all the combinations are stored, and it looks at them up and sends them to right here. So this is an output of it, and this is an input of this combination circuit. So we're actually designing this asynchronous sequential network. We want to design it so that it can't be hacked like the keypads on an ATM or the combination door locks that you see in the movies. So these are the requirements. It doesn't skip from looking for the first combination to looking for the third combination if the first and the second are the same. So it doesn't skip states. If you have a 4, a 3, and a 5, it's going to ask you to enter 4 twice. And it's not going to let you hold the enter button down while the machine scrolls through all the possible combinations to see which one works. Now the state diagram looks something like this, looking for the first, looking for the second, looking for the third correct combination, looking for the fourth correct combination, and then going to this open state and coming back. This is where the safe's open. So this is pretty much a more kind of a circuit. One of the key concepts is that of a stable state. We want one stable state per row. And then we're going to race or slip through some intermediary states to a second stable state. So races can be unintentional, like we saw in design 2, or they can be designed into it, like this. We also saw that in design 2. Now the state diagram that actually ends up being built in this problem looks like this. And our goal is really not to start at this stage and try to figure out why this is what worked. Let's just go straight to the state table. And our goal is to make one stable state per row. So let's just zoom in here and look at this nomenclature. S stands for start. 1F means one combination's been found, 2 combinations have been found, 3 combinations have been found, and then this is where the safe opens up. So this is the output opening of the safe, the electronic lock on the safe or the door. Our inputs are enter and correct. Enter 0, so they haven't pressed the enter button. Correct right now is not the circuit that's responding with the correct combination says no, you haven't entered the correct combination. Here you have entered the correct combination, but you haven't pressed the enter button yet. That's a second stable state. Here we have pressed the enter button, but we have the incorrect combination. That's the third stable state. If we both press the enter button and have already entered the correct combination, then we're going to go down here to the first one found state. The first thing we're going to do after entering the first combination is we're going to release the enter button and we're going to jump over to this column. This column right here is impossible. It's not possible to be here ever. So we're going to jump to this column where we've found the first combination and we're going to slip down to here. And at this point is where we signal to our circuit that's checking combinations to start looking for the second combination. The minute it starts looking for the second combination, that circuit's going to change this value of 1 to 0, and we're going to end up here and slip down to here. So in this row, it's impossible to have the incorrect combination. It's always going to be a 1. And what moves us from this state to this state is that circuit that's checking for that begins checking for the second combination. And you can see we repeat this pattern down here to state 3. We're at this new state and we're searching for the fourth and final combination. If that combination's entered correctly, we move to here, which moves us back up to here. We've got the correct combination, and then if we press the enter button, then we go down to here. So we skip over this state. This is not possible. It's impossible to reach this state. You're going to slip up to here first. So here we open up the safe. We let go of the inner button, slip down to here. And we're going to stay at this state until we enter a wrong combination. And that's what actually gets us to start over again and locks the safe. So you not only have to shut the safe, you have to enter in a wrong combination. This obviously is not the very first state table that came off the top of my mind. This is the final state table after going through all these steps over and over and over again. So I tried to reword the state table, and it looks like this. The not possible states are in these boxes, and I've collapsed these B and C's. Well, I collapsed all three start states into one, and then the B and C is this off blue. The B and C here is this off magenta, and this B and C here is this purple instead of the teal. And then the last two states I collapsed into this open. So this is what we're going to work with. The last part of the implicant table is to do some bounce tests. Did about 5 bounce tests, and this is the result, adding some starts in here. There are 3 or 4 essential hazards found with the bounce tests that were not fixed. So these are the things that need to be checked when testing the circuit. So I wanted to explore the tipping point, what causes us to go the correct path here, and what could cause us to slip down all the way to this bad spot here. So I analyzed everything from a slip point of view and from a bounce point of view. And it turns out the bounce test catches all these problems, this tipping kind of a problem, and frames them correctly. So here's a slip. This is the correct right here, blue, and then here's a slip in red. And then here's the same thing in a bounce. So here's the correct thing here in this teal, and in here is the slip here in red. And you can see the same thing in the bounce. So the cause of the problem and the actual test of the problem are a little bit different, and I just wanted to explore them. We're doing the transition table. I kept the colors the same, but I changed from start to the letter A, one found, right? So that we're losing some of the context of the problem right now, but this helps us build the transition state assignment. So you can see me working through that right here, and I end up with 5 flip-flops. Split this up into 2 4x4s. I visualize A prime as above A and H as above G. And I'm slipping in here into A prime. Keep in mind, you're asking yourself, why? Well, this is a work of art. You know, I build a circuit, doesn't work, and I go back and I fiddle with something. This is why it took so long. This is what I ended up with. Now the next step is to check for races. And I found a couple, and I had to add some states and worry about them. So I had to add this state and this state, these 2 race states, just like design 2. So we finally get to build the circuit. What we're shooting for is something like this. The problem with this circuit is that this is the tie back right here. That's this line right here tying back. And we can't see it. It's sort of buried inside this. Here's another one right here. Here's another one right here. These are the wires we're gonna put delays in if we're going to follow this kind of a diagram. And there's just no way to do it so that it's obvious that this has no tie back and that this is Z. The second thing is that delays are evil in themselves. We don't want them. And this circuit works without any delays. So the big problem in building the circuit is eliminating the static and dynamic hazards, which is basically drawing the Carnot maps and looking for overlapping implicants. And when you have 1, 2, 3, 4, 5, 6, 7 inputs, the Carnot map gets to 128 states. So the next slides are showing me coping with that. The first thing I did is I took the excitation table and I put it into a spreadsheet. I just mentioned the rows that are full of data and skipped all the don't cares. So this dropped me down from 128 to about 60 rows. The second thing I did is I typed all this stuff into Logisim by hand. And then I cut and pasted out of Logisim, highlighted in color the same regions, and then compared them to make sure I didn't make any mistakes. That's this slide and this next slide. This is the logic that came out of Logisim. And then I used this, just like I did in Design 2, to go off and build the Carnot maps and check for static and dynamic hazards by looking and making sure that all the implicants overlapped. And again, like Design 2, I found just one that needed to be added. So I'm going to show it to you working. When you open it up the first time, you'll see some of the red. And all you need to do is bounce on these switches until it turns green. Then what you can do is delete that switch and just get the correct combination value coming in. Now this is what we're looking for. We're looking for the first combination. All right. Looks like we found the first combination, and now we're looking for the second one, because the first combination was 0, 0, 0. Everything's 0, 0, 0 right now. So let's add combinations that look like this. And right now we're entering 0, 0. So if we press the enter button, it's going to say wrong and start us all over again. Yes. And we'll stay here forever until we enter the right combination. So I'm entering the right combination. It's that one right there, putting right here. That makes the correct line go high, and you can see the states changed a little bit in here. Now I'm going to press enter, and we go to the correct comment. We acknowledge that we found the first combination, and now we're looking for the second one. Okay, so let's put the second one in here. Yes, and it goes correct. Now when I press enter, and you can see the states changed a little bit, and now we're looking for the third combination. Okay, so let's enter the third combination incorrectly. Yes, it went correct. All right, pressing enter. And now we're looking for the fourth. Once we find the fourth, then it will unlock. The fourth is 0, 0. Okay. Here's the fourth. I'm pressing enter. And it's unlocked. Yes. And we're going to stay here until we enter a wrong combination. And then instantly it goes back. This is an asynchronous sequential network working. So let's take a tour of it a little bit. The ASN network looks like this. This is the combinatory network that maps the 5 flip-flops into 2 bits that document which combination we're looking for. Combination 0, combination 1, combination 2. This is the main circuit right here that we were working with. So I encourage you to download this and play with it.